Hello, everyone. Thank you for joining us today. My name is Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. We'd like to begin today's webcast by saying a big thank you to VoltDB for sponsoring today's event, and let you all know VoltDB is an in-memory NewSQL database purpose-built to power a new generation of applications that thrive on fast, smart data. Tapping the lightning speed and real-time analytics of VoltDB, organizations are able to add context and intelligence to data the instant it arrives to make real-time transactional decisions that will maximize its business value. The relational database is architected to meet the distinct requirements of fast data, which leads to big data. Organizations in markets such as mobile, financial services, energy, advertising, security, and gaming are relying on VoltDB to process smart data fast to capture new revenue opportunities, drive competitive advantage, and create highly specialized interactions. VoltDB is privately held with offices in Bedford, Massachusetts, and Santa Clara, California. Today we have Professor Michael Stonebraker of MIT, co-founder of VoltDB, and Scott Jar, co-founder and chief strategy officer of VoltDB. And they're going to talk to you about big data, fast data, the need for in-memory database technology. Mike was the main architect of the Ingress Relational DBMS and the Object Relational DBMS PostgreSQL. These prototypes were developed at the University of California at Berkeley, where Stonebraker was a professor of computer science for 25 years. More recently at MIT, he was a co-architect of the Aurora Borealis streaming process engine, commercialized as Streambase, the C-store column-oriented DBMS, commercialized as Vertica, and the H-store transaction processing engine, commercialized as VoltDB. Currently, he is working on science-oriented DBMSs and search engines for accessing the deep web. He is the co-founder of 6 venture capital-backed startups. Scott brings over 20 years of experience building, launching, and growing groundbreaking software companies. In 2010, Scott co-founded VoltDB after realizing the opportunities available to businesses that could effectively use data to impact the world. Prior to VoltDB, Scott founded, served as board member, and advised several early-stage companies in the data, mobile, and storage markets. Folks, we're really excited to have Michael and Scott with us today to present this webcast for you all. As we get the event started, I'd like to go over a little housekeeping to help you get the most out of today's webcast. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Michael and Scott. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Michael and Scott, please preface them with a capital letter Q so we know that it's for them and we can make sure we see it for Q&A. You can also open, move, and resize any of the other widgets. If you'd like to tweet from the Twitter widget today, you might need to give it permission to access your account. The Twitter widget will automatically append the event's hashtag to your tweet so you don't have to. And today, folks, we have 2 hashtags. First one is VoltDB, and the second one is StrataConf, all one word. If you have any trouble with the webcast, please take a look at your help widget. If you continue to have trouble, just post it in the group chat, and one of our staff will help you right away. If you have any choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is close any apps that could interfere. People always ask, so we'd like you to know we are recording today's webcast, and we will have the archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Michael and Scott. Hello, gentlemen.
Good morning, Yasmina. Thank you very much for the introductions. Mike and I are thrilled to be here to talk to you all today. On the screen here, we have the overview. This is what we're going to go through in the next 40 minutes or so, but we would love to have a bunch of questions at the end, so we're going to save a bunch of time so that we can address those questions. As Yasmina said, there's always a lot of very interesting information that comes about. So I'm going to talk in the beginning a little bit about fast data, what we term as sort of the new big data and why it drives big data that we see in the organizations. Talk a little bit about what that architectures that we see customers of ours as well as players in the market generally starting to build to address these new challenges around data, whether it's big or fast. And then Mike's going to take us into a dive into what it takes to architect databases to solve these needs, because as everyone has really come to acknowledge, one size doesn't fit all. And then at the last major section here, Mike's going to talk quite a bit about why Volt is an ideal and optimal solution for dealing with streaming data. So with that quick overview, let's dive right in here and start to talk about some interesting things that we see in the market regarding data. So I love this little graphic. This is my reference to a state-of-the-art search engine, our recommendation engine. So our little old lady here that's in the grocery store, she goes and is buying bananas. And the idea that we're able to take data based on others' purchase history and make recommendations to her. The information in this silly example, it's quite relevant, right? She's in the purchase cycle, so it's timely. But it's really not personalized to her. So we're suffering in this example with the ability that we're choosing timeliness. You know, she's shopping and therefore about to make a transaction and a purchase, so the timing matters to her. But it's not really a personalized experience. Maybe she's making banana splits as opposed to banana bread or some such example. But the idea is that we're really looking at the difference between trading off timeliness versus accuracy. The sort of corollary to this is, you know, if there are tremendous amounts of data in very sophisticated search engines and recommendation engines that if we wanted and we took the time today, we could probably find the absolute ideal thing to recommend to somebody. But it takes time, and timeliness then is traded off for the accuracy. So if we're going to now send, I buy something on Amazon and they're going to send me a recommendation, and the next day after they've run their overnight analytics, you know, I might be at the beach the next time, or I'm going to be in the mountains this coming weekend, and I'm not going to get that email. So the timeliness is off, and the context is really skewed. So I'm going to give you one more example, and then we're going to talk about this trade-off. So this picture, for those of you that recognize what it is this is a miner carrying a canary. So this was I like to term this as one of the ideal first big data systems. Right, that canary was a fantastic data ingestion engine. It was really good at making decisions, and it had a very visual experience to it. When the canary fell off his perch, the miner knew something was wrong. So there's a lot of timely data here, but we really have moved beyond what we can do there, and now we're seeing, and this is actually a live example that we have, we see these huge sensor deployments within mines, and miners now wear jackets that have, you know, a myriad of sensors on them to ingest information, make decisions. But again, that information becomes much more valuable when it's aggregated with other people. So how do we take this real-time data that's occurring in the mine, aggregate it with other miners, you know, so that there's not a misread of a sensor. I exhale into a sensor near my chest, and therefore it sees a low carbon or a high carbon monoxide, carbon dioxide reading, and therefore it sets off an alarm. Well, it might have been just me breathing in an odd place, but what happens if I have 5, 6, 7 miners that have the exact same reading that's trending in a certain way over a course of 30, 40 seconds? Now all of a sudden I'm starting to take the value of data and I'm realizing that, hey, there's a problem here. So what we really are sort of wondering to ourselves out loud is, you know, are we forced to choose between these two things? Are we forced to choose either timely information, where I have to use sampled recommendations, or I'm taking inaccurate readings from a sensor, or maybe I'm finding some of the fraud that's happening in my systems right now? Or do I have to choose between that or the fact that I'm using, you know, accurate or smart information? You know, a suggestion after the purchase, it's no longer timely. Those types of things. How do I catch all the fraud, but it's after the fact and now it's forensic information? So what we're going to start to talk about is is this really a trade-off that exists in the market, or are there solutions and ways to solve this? And, you know, I think that the analytics stack in general is really starting to take some shape in the market. There's a lot of commonality into the deployments that I see out there. I see this general idea of a data lake, call it a data reservoir, call it whatever you want, but the idea that it's a dumping ground for all my corporate data. We're starting to see a lot of that commonality in places. And we're also starting to see a really clear growing of what the ancillary components to that data lake are. We're going to have BI reporting through some of these great data warehouse stores. We have SQL on Hadoop to do some other types of querying into that data lake and exploratory. And there's a lot of things there that I'm not going to spend a lot of time going into, but I think most of you, given the type of personality that's on this call, you understand or you've seen these things. And we're starting to really see this form around the data lake. And of course we have you know, our enterprise apps. So if the data lake's going to hold everything, it's going to have to hold the data from our enterprise apps as well. So now we start to have this analytics stack that's really starting to make a little bit of a focus into how we're going to build these systems. But the reality is why do we do these analytics? You know, I've been saying that for years now, the only reason to do analytics at any point is to make a better decision. Well, it's a better decision, it's a better personalization, it's a better recommendation, it's a better warning to a miner, it's a better detection of fraud. All those things are the reasons that we do analytics. But the question then becomes is when do we do those things? Well, there's infinitely more value in those decisions and those recommendations and those detections when I can actually do them in real time. The closer to now that I'm doing them, and the less forensic they become and the more actionable they are. So with that, I kind of wanted to set the stage with this poll question, and we love the interaction on these, and we'll sort of try to see how that plays out into how preceding slides come. But the question that we have put forth here is, so what is the thing that is putting pressure on your company's data system? So we're all experiencing, you know, data that's crushing our systems, but what is the cause for that? And Yasmina has pushed this poll question up with the answer. So I'm going to give you about 30, 40 seconds to answer this. And again, we really love the responses because it starts to make this interactive, and also we can really talk to some of the core issues that are in play today. So as people are filling this out, just a little bit of context to these. You know, are you dealing with new sources, new streams of data that are coming in? Do current applications need more activity because of business needs or because of user desires? Are we looking for faster analytics? Businesses are asking for more analytics, or analytics becoming more operational in nature? And lastly, is there interactivity between applications that's causing this? So here we go with some results, and I think this is, no surprise here, right? This is very indicative of what we're seeing today. You know, the idea that there's a lot of streams out there is very much the case. Interactivity within those streams, and then the business then saying, hey, I need these analytics faster, whether it's for dashboarding or for its real time. So I'm going to move on to the next slide here and really make the case that based on those results, what we're seeing is that application and analytics are no longer developed separately. Right? It used to be the case that we develop an application, it would store its own data. At some point we'd go through that ETL process and somebody would say, geez, we should run some analytics on that. That does not exist in today's applications. The applications are built at the same time or designed at the same time that we think about the analytics, whether those analytics are operational in the way that we're viewing dashboards or whether they're part of the decision-making process. And yeah, it is crazy, it's ambitious, it's a hard thing to do, but that's why these new data systems have come to the forefront, enabling people to make these decisions and build these types of applications. So now if you take the context that says application and analytics are built together, the question then becomes, well, what do our data systems need to do to be able to enable that? And through the course of since we've launched Volt and talking to so many customers and so many people challenged with these types of problems, we found that there's really three things that are really driving these systems and putting so much pressure on them. And your answers to the poll questions very much illustrate this. Number one, you know, this was one of the highest ranking on the poll question. I have to ingest huge amounts of events. Streams of data are coming in faster than my systems have been able to manage. I've got to get them into a system very quickly. Number two, even though they're just coming in, I don't want to land them on disk and worry about them later. There's value in me making interactions with them. But those interactions really need to be data-driven. How do I use past history? How do I use context? How do I use other data sources to make data-driven decisions on this? You know, if we're talking database lingo here, that would be transactions. How do we do transactions on data that's coming in at these kind of rates? And then lastly, I need to analyze this information. This was the second high item on our poll question. I need to analyze the information that's coming in real time. And that becomes something that might be end-user facing, gaming leaderboards, or it might be something that shows up to our mining operations guys who are looking at all the data that's in the mine and how people are living in the mine and working in safety levels and constraints. So these are the three things that really take data that's fast and start to make it very smart data. So if we move back to our analytics stack and we see this, now all of a sudden what we've built is we've built this fast data component. So fast data, as Yasmina introed in the beginning, is what's driving big data. We don't get big data without it coming in fast. So in fast data, we have the things required here that we just talked about in the previous slide. I'm ingesting it, I'm making real-time decisions and transactions, and I'm doing real-time analytics on it. Even further, let's take this arrow that moves from the right to the left, and we're saying, you know, we get knowledge, we get data, we get results from our analytics systems. We can feed those back into our operational fast data systems, and what does that allow us to do? It allows us to serve dashboards very quickly that we wouldn't have been able to do. It allows us to make smarter models. It becomes a closed-loop system where our operational interactions are being enhanced and informed by our analytics, and all of a sudden we have a very fast system that does both big data and fast data. And the thing that I'll say about this is if you look at it, all of a sudden what you realize is that's an operational database. It just happens to have the kinds of orders of magnitude of performance that we haven't seen before. And now all of a sudden you say, if I can solve this problem not with a stream processing tool, not with batch jobs, not with caches on top of caches, but with an operational database that's fast enough to manage it, all of a sudden this architecture starts to become a reality, and we can build these types of applications. So this is a great segue to start to hand it off to Mike, because if you look at that picture and that diagram, this fits very clearly into what Mike's been saying for the past decade and a half, that you have to special purpose build a database for those applications. Fast data is distinctly different from big data. So architecture is important. If you're going to go high performance, which all of these apps are, make no mistake, your big data apps are high performance in one way or another. If you're going to do that, architecture matters. And so at this point, I'm going to hand it off to Mike so that he can talk about why he built Volt the way he has, and some of the architectures around some of the additional analytics capabilities in the other systems to get us to the point where we can solve this architecture in a single system. So Mike, off to you.
Thanks, Scott, for that introduction. What I want to do is tell you about basically how to build fast database systems. Now, I want to preface this with for 30 years or so during the 1980s, 90s, and into the early 2000s, there was a concept called one size fits all. If you called up your Oracle salesman and said, I have a database problem, he would say, well, Oracle 9i, 12g, 13h is the answer. Now, what was your question? So the elephants were peddling one size fits all. And I wrote a pioneering paper in 2007 that said one size fits all, an idea whose time has come and gone, which claimed that you needed multiple purpose-built systems. I'd make a stronger statement in 2014, which is one size fits none, which is the elephant's code lines are now legacy systems that are not good at anything. So what I'm going to do is quickly tell you what it is that you buy from the elephants. And those are companies with 3 letters in their corporate name, 9 letters and 6 letters are the major players. And unless you squint, they are all selling you the same thing, which is they're selling you a relational database system that stores records contiguously on disk. So what happens is the next thing in storage is the next field in the same record. So that's what's called a row store. They all use B-tree indexing. That's the gold standard for indexing data. They use relatively small disk blocks that are heavily encoded. So your data lives on disk, and it lives in encoded disk blocks. Oftentimes, they align fields on byte or word boundaries, and the technology for query execution and optimization dates from 1979 in a pioneering paper by Pat Selinger. In the mid-1990s, C. Mohan, who's a researcher for IBM, wrote a pioneering paper called ARES, which describes how to do crash recovery using write-ahead log technology. The ARES scheme of things has been adopted by all of the current relational database elephants, and everybody has synchronized on doing row-level dynamic locking for concurrency control. So that's what you get if you get a system from any one of the elephants. And I will just call these a row store, and all the major vendors are happy to sell you a row store. Now, what I want to do is tell you why that architecture won't work for modern OLTP databases and modern streaming applications. So I have 3 reality checks I want to explore with you. The first one is your streaming databases aren't that big. Historical data warehouses are truly gymongous, but transaction processing databases grow at the rate that your streams increase in velocity, or at the rate you are executing more transactions. So I've talked to a lot of people with these sorts of databases, and a terabyte is a very big transaction processing database. There's very few applications that require more than a terabyte. So if you want to go fast, all you have to do is invest about $30K, and you can buy a terabyte of main memory. So think of your databases as main memory resident. So you say, well, maybe my data doesn't fit right now. Well, memory prices are going to continue to decline. So if you don't fit now, then wait a couple of years and you will. So main memory is in your future. Now, some of you are about to explain to me that Facebook has a truly gigantic OLTP database. And yes, they certainly do. They have one of the hardest transaction processing problems on the planet, and it's certainly an outlier. And they are scratching their heads trying to figure out how to keep up with their load. But think main memory. That's reality check number 1. Reality check number 2 is you've got to think about the way you handle interactions with a client. So historically, we all used ODBC and JDBC, and that's a very, very heavyweight protocol. And if you want to do 30 transactions a second, it's perfectly adequate, but it has way too much overhead if you want to go really fast. So you need a lightweight protocol that's asynchronous, that does connection pooling, and for sure you need to do a stored procedure interface. And if you do vanilla traditional ODBC or JDBC, that will be the high pole in your tent, and you will go exactly at the speed that you can get transactions through your client interface. And just as an aside, Microsoft and others have recently released main memory database systems, but the Microsoft one is called Hackathon, and it's in SQL Server 14. And Microsoft marketing said you have to put this underneath the covers and make it look like it's inside normal SQL Server. and that means they forced the traditional client interface on Hekaton, and that is the high pole in the Hekaton tent. So reality check number 2, beware anybody who says just use ordinary OEBC or JDBC. Reality check number 3, this turns out to be data from a paper that I and others wrote in 2008, and we timed TPCC, which is the traditional transaction processing benchmark. We timed it on the Shore DBMS prototype, mostly because we had the source code, and Shore is a system that works very much the way the Elephant's products work. And we said, where do all the cycles go on the assumption that all of your data lives in the buffer pool in main memory? And here is sort of the artist rendition of roughly what happened. And what exactly happens depends on which TPCC query you're running. And so, unless you squint, more or less the useful work is way under 10%. So any database system will spend 10% or less on actually executing your transaction. The rest of the 90% is in 4 very large pie slices. The first one is buffer pool overhead, which is you've got to get a record out of the buffer pool. When you're done modifying it, you've got to put it back. You have to maintain an LRU list of buffer pool pages. You've got to pin pages. All of that stuff is intensive in CPU overhead and is about a quarter of the overhead. Dynamic row-level locking, every time you touch a record, you have to set a lock. Every time you write a record, you have to upgrade that read lock to a write lock and so forth. That's another big slice of the pie. Third slice of the pie is Aries write-ahead logging. At runtime, whenever you modify a record, you have to put the before image and the after image into the log and make sure that that log record goes out to disk before the data goes out to disk. The runtime cost of write-ahead logging is another big slice of the pie. The last slice is a little bit counterintuitive. It turns out that any database system, or most database systems, and all of the traditional ones, have a lot of shared data structures. The lock table is a shared data structure. B-trees are a shared data structure. With the advent of multi-threaded computing, which comes about because I have a whole bunch of cores that I want to keep busy, then I've got to latch these shared data structures to keep them from getting corrupted. And the latching overhead makes threads wait. And so that's another big slice of the pie. So there's 4 big pieces of overhead and a little bitty sliver of useful work. So now you think about this for about a millisecond and you say, if I want to go fast, well, I can invent better data structures. And there are things called fractal trees. There are improvements to B-trees. These things affect the 4% slice of the pie. So if you do 50% better at data structures, you will go 2% faster. This is completely irrelevant, except for specialized tasks like bulk loading. To go fast, you have got to address the sources of overhead. Now, the next thing you have to think about is if you get rid of all 4 slices of the pie, you go faster. But if you get rid of a lesser number, then you do less well. So, for example, Oracle has had a main memory database system called x10 that they've been selling for more than a decade. It is a main memory database system, so there is no buffer pool. That slice of the pie is gone. However, they continue to use row-level locking. They continue to have an Aries-style write-ahead log, and they continue to be multi-threaded, which means they have this latching problem. So 3 slices remain, 1 slice is gone. So the implications of this are on the next slide, which is if you have all 4 slices remaining in your pie, then the elephant's traditional code lines will go at, I call it relative performance 1. If you get rid of 1 slice of the pie, which is what times 10 has done, you go about 30% faster because the other 3 slices are still there and become the high pole in the tent. If you get rid of 2 of the slices of pie, you basically go twice as fast. If you get rid of 3 of the 4 slices, then you go 4 times as fast. And if you can get rid of all 4 slices of the pie, you go 25 times faster. So it's an obvious no-brainer that if you're going to build a purpose-built database system, you've got to get rid of all 4 slices of the pie. Anything less than that, and it's a marginal win. So in the rest of my time with you, I'm going to tell you how it is you get rid of all 4 slices of the pie. First one is you got to get rid of the buffer pool. Any main memory database system will do that. Any disk-based database system is going to lose. It has that slice of the pie remaining, and it will have an upper bound on how fast it goes. So all of the NoSQL guys are disk-based DBMSs with a buffer pool. All the elephants are disk-based DBMSs with a buffer pool. They're fundamentally going to lose. So you've got to run a main memory database system. Next slide. Now let's turn to Latches. As I said a few minutes ago, a DBMS has lots of shared data structures. And you can read about them on the slide that's on your screen. And they're just insidiously everywhere. So that means that any multi-threaded system is going to have a lot of short-term locks that are going to cause performance problems. So if you want to get rid of the latches, you've got 2 things you can do. If you run multi-core, you need latches to avoid corruption. And in a many-core world where we're quickly heading, you are going to have yet more threads alive, which is going to make this problem worse. So there are only 2 solutions that I know of. The first one is run single-threaded code, and that's exactly what VoltDB does. It is not multi-threaded. If you're not going to make single-threaded code, you've got to somehow invent latch-free data structures. There's a lot of research in this area, which is so far focused mainly on indexing and on concurrency control, and that's only a small subset of all the shared data structures that you've got to deal with. So essentially all systems written more than a decade ago are going to have a big problem with latches, and modern systems that have been written recently, such as VoltDB, have got to have some solution. What VoltDB uses is single threading, and therefore we get rid of that piece of the pie. Now let's turn to the necessity of doing crash recovery. So I'm going to give you some quick data from an MIT graduate student named Nirmesh Malvaiya. This is from a paper in the ICDE proceedings of this year. He implemented standard write-ahead logging in VoltDB and compared it against the VoltDB scheme. What does VoltDB do? Well, we take asynchronous transaction-consistent checkpoints, and then we realize that if you're going to log the data, that will be way too slow. So what we do instead is we log just the transaction that you ran. So if you go up to McDonald's and you order a number 6 with fries and a Diet Coke, what VoltDB logs is 6 fries, Diet Coke. that's a much smaller amount of data than the effects of that transaction, which is much, much larger. And we do group commit so that we do this as infrequently as possible. So we timed what we do against what Aries would do. And the next slide shows you a picture. And what you can see is there's the performance of Volt with no logging at all. That's the top dotted line. Slightly below that is this command logging scheme, which is what we currently do. It costs you a few percent to actually do crash recovery, but it doesn't cost you very much. If you do standard data logging, then it costs you about 50%. And that's because the slice of the pie, way back from that pie diagram, it becomes a big problem when it's the only slice of the pie that's remaining. Of course, there's no free lunch. What does command logging entail? Well, when you recover, we actually rerun your transactions so that it will take us longer to recover than it will take an Aries-style system to just roll the data forward. So we run about 50% slower at recovery time. And the thing that you should note is that you have a trade-off. You can either pay 50% all the time, or you can pay it just at recovery time. But the thing to realize is that essentially all Volt customers run high availability. They run replication to have multiple replicas, and we fail over and just keep going if there is a problem. The only time you ever have to run actual recovery is if you get a cluster-wide failure, and the power goes out every now and then, I agree, but it's maybe every few months. So VoltDB makes the rational decision to go 50% faster at runtime at the expense of every once in a blue moon, it's going to take us longer to recover. What's the last slice of the pie? Well, that's concurrency control. No one who's written main memory database systems uses row-level dynamic locking. It is too slow. Multi-version concurrency control is popular. Timestamp ordering is popular. There are a variety of other schemes. The thing to note is no one is using dynamic locking. So if we go to the next slide, which gives us the net-net, is that if you run the Volt scheme, we do crash recovery, basically 50% faster than the elephants. We have a very high performance, high availability system, which I didn't get a chance to talk about because we don't have a whole lot of time. That's worth another factor of 2. And if you get rid of all 4 pie slices, that's worth a big factor. Net-net, we go about 100x faster than the elephants on this class of problems. And the thing for you to realize is that if you care about performance and you want a factor of 100, come see us. If you don't care about performance, well, run whatever you want. If you want to do 30 transactions a second, your wristwatch will probably be happy to run 30 TPS. If you pick up most any database textbook, it will tell you all about row-level locking and Aries-style write-ahead logging and multi-threading and latches, and all that stuff is obsolete. Modern OLTP database systems don't do any of that stuff. So if you pick up a textbook, it's probably totally obsolete. So what I'd like to do now is take a pause before we talk about streaming applications. And Yasmina is going to insert another poll question. And so this concerns what it is that you need out of your performance-constrained DBMSs. And there are a whole bunch of possible answers, which hopefully Yasmina is going to put up right now. And so you can say, I need more transaction throughput. You can say, I need faster real-time analytics. You can say, I need faster business intelligence reporting. You can say, I need larger data. Everybody should say, I want lower cost. All of the non-open source elephants are ridiculously expensive. And if you're happy, you can answer none of the above. And if you're happy, then you should go find something else to do with the rest of this hour, because that's not what we're talking about. So now I have to fill up the next 20 seconds or so while the numbers come up. And so what the most popular answer is faster and cheaper, which is exactly what you would expect. And so VoltDB is an open source system. Feel free to download it and run it. It's free unless you want support, and then it's cheap, and it's blindingly fast. So now let's turn to talk for a few minutes about streaming data, which is traditional OLTP assumed that transactions were coming in from humans or from terminals. But that's often not the case these days. Transactions are often coming in from the Internet of Things, meaning they're coming in from sensor technology. They're also coming in from other kinds of places, like massively multiplayer Internet games, where you have a great number of humans who are interacting with the game and giving you very high transaction rates. So if you have streaming data, well, there's two kinds of applications that you tend to want to do. The first one is you want to find patterns in what players are doing. So find any player that is shooting and moving at the same time, or find me anybody who's exhibiting antisocial behavior by doing something that the game vendors don't like. So you're looking for patterns in a fire hose of incoming stuff, whether it's from the Internet of Things or from multiple players. Historically, this has been the realm of complex event processing systems, CEP. So in contrast to patterns in the fire hose, the next application is that I want to keep, for example, a leaderboard of the top 20 players who are playing this game. That means I have to maintain state. And if I want to maintain state, I've got to make sure I don't lose any messages. And anytime I'm interested in calculating a metric that deals with the game, I'm interested in reliably maintaining state. This is the sweet spot for VoltDB. It will transactionally keep your state. It's also pretty good at doing patterns in the fire hose, but the sweet spot is things that involve maintaining state. So the next slide says most applications that I can think of need to reliably maintain state. I don't know of very many people who are happy to lose state. Some applications are willing to lose state. Most of them aren't. So I think God is on my side. Most streaming applications are the kind of stuff that Volt is really good at. So what do we allow you to do on streaming data? Well, there's three kinds of things that you typically want to do. You want to process messages without ever losing them. So don't lose my message, and do something with an incoming message. Either update the leaderboard or whatever else it is that you're trying to do. Occasionally, people want to run normal SQL queries. In a stock market application, I might want to find out what my position for or against IBM is. And lots of people want to do windowing operations. Find me the moving average of the number of players on my game, or find me the 1-minute moving average of IBM stock price. VoltDB is happy to do windowing operations, happy to do normal SQL queries, happy to transactionally process messages. We do great on streaming data, and we are sort of, we don't care whether your data comes in from humans or it comes in from the Internet of Things. So streaming data works fine in VoltDB right now. Volt is blindingly fast. You want to go yet faster than simply scale out over a greater number of nodes. You'll get higher velocity. We will linearly scale as you increase the number of nodes that you allocate to VoltDB. So with that, I'll stop right here and let Scott give you the last couple slides to wrap up. So Scott, over to you.
Thanks, Mike. As always, awesome. If nobody tweeted the fact that Mike said that if you need to do 30 transactions a second, you could do it on your wristwatch, and shame on you. That was one of my favorite Mike quotes ever, I think. It was great. So, we talked a lot of theory in the beginning as to how big data applications are being developed, and Mike talked a lot about the academic and the architectural reasons to do what we've done at Volt. I wanted to just quickly here talk about some of the results that we're seeing. As we talk about a lot of our customers, there's a tremendous amount of great results that people are getting, things that are very tangible. So, I've listed a number here, 4 or 5 of them. But as you can see in each one of these, and I don't intend to go through them, but as you can see in each one of these, there's really something that fast data and the ability to do transactions and real-time analytics on these very fast inbound feeds is allowing people to either make better decisions, to save money. That was one of everybody's top requirements in one of their poll questions. The top one, they're able to detect 100% of the DDoS attacks as opposed to some smaller percentage. People are saving money because they've gotten rid of the elephant systems, as Mike has mentioned, being so expensive, and they're reducing costs. So lots of very tangible business advantages, but there's also, as you know, a lot of very tangible technology advantages. So one last slide that I want to just quickly talk through, and then we're going to jump over to questions because there were quite a few questions. I was frantically going through them, trying to prioritize them. So there'll be some fun questions and conversation to have after this, Mike. So really quickly, the only reason that I wanted to put this slide in here is not to brag about the logos on the right, but to really look at the things on the left and say, people often ask me, well, I get the fast data, I get that we're doing things on the inbounds and the transactions and the analytics, but where do those use cases exist? And I can tell you this is only a small subset of where we're seeing these use cases exist. Personalized targeting is huge. It doesn't exist purely in digital advertising or internet retailing. It exists in medical records. It exists in interactions on sensors. It is a very large-scale problem that people are struggling with today. Telco, we have a lot of customers that are doing many things in that area, again, all because fast data is coming in. Talked about a very interesting sensor application in the mining environment, but there's also a lot of stuff that is going on the Internet of Things, smart grids. We're doing a deployment where the UK is rolling out 53 million smart meters. Guess what? That's a fast stream of data that very real-time decisions need to be made on. Data cleansing is an example of that. So, taking smart meter readings in and figuring out how to clean and enrich that data prior to it hitting your long-term data store. And then the last one, just to touch on here quickly, is infrastructure. When we started Volt, most of the things that we saw were in those top 4 and other categories that were very specific use cases. We're now starting to see a much higher interaction of people that are building infrastructure applications. When you look at logs, for example, logs are a great system, for delivering real-time data. Logs are not naturally a batch process. It's a real-time streaming process. Once I can start to look at logs, I can figure out system performance, I can figure out web performance, I can figure out ad targeting, I can do all these things, and when I can do them in real time and simplify the infrastructure, I'm building data pipelines, I'm looking at streaming performance, and I'm doing inline real-time ETL, and we're seeing a lot of people doing that today. So again, quick overview of some of the fast data problems, and with that, I'm going to hand some questions off. Mike, I'm going to, most of these look like ones I'd love for you to answer, especially with the background that you have with Volt and many of the other databases. The first one, which my favorite zoo question that I think I've seen here, it says, Mike, by elephants, you do not mean Hadoop. You mean gorillas, right? I think I thought you'd appreciate that.
Yeah, I can give you a totally separate rant about Hadoop, but Hadoop is used for batch processing problems, which it does them very badly, and by the elephants I mean the traditional relational database vendors.
So we got a question that says, is Volt columnar? And I think that was answered after this question came in. But the follow-up part to that is, if not, then how does performance of aggregation queries compare to columnar databases such as Vertica?
Okay, so the if all of your data fits in main memory, which it does with VoltDB, so we have to, if you're running an aggregate, we have to paw over a column of data. However, if you want to find the average of those employee salaries who are in the shoe department, you're also filtering the data, which means you've got to get at a different attribute in the same record. So in main memory, column stores and row stores will run at about the same speed. So the real question is VoltDB faster than Vertica on data which fits in main memory? The answer is, if you are I/O bound, VoltDB will run faster. If you are CPU bound, both systems will run at about the same speed.
And do you want to touch on the materialized view aspects too?
Go ahead. I'm not sure what you're referring to, so tell us.
Sorry about that. Yeah, as designed into Volt, there's a capability for materialized views. So we're paying the penalty, so to speak, of updating aggregates, counters, leaderboards over the process of each transaction. So we're amortizing that cost. And then when you go to do an analytic that looks at one of these materialized views, the views come up in a very fast format. So we're finding that a lot of our customers are actually using Volt's materialized view capability for those types of quick running analytics. So Mike, another question here. How does Volt deal with node failures?
Okay, so node, basically tandem computers way back when, in the 80s, basically what they did was they failed over to a backup, and that's exactly what we do. We make sure that if you replicate your data, we make sure that every record is, every replica of every record is on a different node than the primary. So if there's a node failure, there's a complete copy of everything elsewhere. And we simply fail over and keep going in roughly the same way Tandem did it way back when in the 80s. And then we configure the dead node out of the Volt system. So you're now running with n-1 nodes. And in aggregate, you will see the performance deteriorate by about 1 over n, because the amount of computing resources you have has gone down, you will replace the dead node one way or another, and then you'll tell us that the new node is exists, and we will then bring the dead node in background up to speed, so that over time you will all of the transactions that the dead node missed get played. And when it's current, we will then flip a switch, and you're running with n nodes again instead of n-1. All of this is completely transparent. You don't have to do anything. It just works. So you will never notice, a user will never notice that a node failed, except conceivably with a very, very small hiccup while we're flipping switches around.
So there were a number of questions around moving data from Volt into another data store, and since that was in the section that I talked about, I'll hit on that. And Mike, please feel free to elaborate anything that you want. So Volt, as we sort of talked about the fast data and big data as two categories, we early on realized that the ability to move data between those two environments was going to be a critical function of the Volt system. So we've built a rather sophisticated ability. We call it export, but think of it more as effectively it's a table type within Volt. And by using that unique table type, we allow the application to put data in there, and then it can seamlessly move into a variety of back-end systems, whether that's Hadoop or a Vertica or a Netezza or a Greenplum or any other back-end system. And it allows for a lot of flexibility in how to get data in and out of Volt, as well as really using common architectural building blocks. Kafka, for example, is a system that we've adopted quite a bit on both the import and the export side of Volt. Mike, did you have anything to add to that one?
I say we're happy to export to a variety of systems. And the thing we find is that we can export data faster than whoever is downstream can ingest it. So usually we are never the high pole in the tent in getting data into the downstream system. So we'll run at whatever the speed of your downstream system is.
Yeah, a great point. I should have mentioned that. Absolutely. And in addition to that, we're able to batch things up so that it's in a way that's more digestible to those downstream systems. We've done that a number of times for particular use cases. So, Mike, Jim asked, what's the best way to do data cleaning from real-time data streams that are coming from multiple data sources with Volt?
I think so let me answer that question in two different ways. If your data is dirty and you know how it's dirty, so you know that Scott Jar is Jar followed by a comma followed by Scott. So you want to simply flip first name and last name and remove the comma. So all you have to do is ingest the data into Volt and then run a SQL command to flip stuff around. So you can do any cleaning you want in SQL inside of Volt at the speed Volt can do stuff. The bigger problem, though, is suppose you don't know how the data is dirty. So you see S followed by C followed by Jar, and the next thing you see is Scott and then Jar, and you're not sure whether these two records are actually the same thing. So then you're in the realm of having to do user in the loop data cleaning, and you're not going to run at VoltDB speeds. So the answer is just do cleaning in the engine using SQL unless you don't know how the data is dirty. And if you don't know how the data is dirty, then you've got a much bigger problem.
Great. So there's a ton of questions here. I'm going to try and sneak a couple more in. I know we're at the top of the hour, but I think we can get a couple more in. And there's one particularly that I'd like to save for the ending. I think it's fitting for you, Mike. But a couple really quickly I'll address. How do you scale out in a cluster? And Volt was designed from the very beginning, even in the HStore papers, that the system and cluster would automatically grow as needs increase. So you'd add more nodes to the system, and the system would rebalance. And in recent versions of Volt, we've actually added the ability to do that on the fly. So if you want to move from a 10-node system to a 15-node system, you add 5 more nodes. The system starts to repartition itself all automatically, all in the background, and it becomes 15 nodes. So the system really is designed for that type of scale-out capability. Is there a persistent data store component to VoltDB? I think that's a really good question. VoltDB is a persistent data store. So we have built persistence into the system in a number of ways, one of which, as Mike references, is the HA side. We ensure that data is on X number of nodes. You choose X before we consider that data to be safe. But we've also added the ability for disk persistence in both snapshots, which are periodic writings to disk of the data, as well as the idea that Mike went into some depth on called command logging. So command logging will ensure transactional durability to disk at either a synchronous or asynchronous level you choose based on your application performance needs. There are, in fact, ODBC and JDBC drivers. There's JDBC available for Volt now. ODBC is very short time frame before that's available. That's coming out soon. Again, many people use that to connect to visualization tools as well as other data management tools. I'm trying to hit a couple of these very quickly. Somebody asked a question about one of the use cases that we have had up there. How do you increase free-to-pay conversion rate? And I like that question because it's very specific to a use case, but it has very generalized applicability. The moment you know more about your users and can interact with them in real time, the much better you can do at click-through rates, at in-game monetization, at increasing after-sale components. All these things are because we're able to add more and more capabilities into the decision-making process at a particular point in time. I'll give you one example in addition to this gaming one where the free-to-pay conversion rate was increased is a digital advertising company that was at one time when we started interacting with them, they were only using 2 data sources to place ad inventory. And with Volt, they were able to achieve speeds that allowed them to increase that to 12 data sources. And at that point in time, moving from 2 data sources to 12, knowing more about their customers, more about the interactions, they increased their click-through rate and thus directly their conversion rate and their revenue by 83%. So that's the kind of thing you can do as you start to get far more capabilities and far more knowledge about your users because you're able to interact with them right in relevant information in a timely manner, the thing we very much started with in the beginning. So Mike, last question here, and we're going to have to email the group the answers to the remaining questions. There's probably quite a few still left here. But the last question that I kind of wanted to give you at the end is somebody asked you to look in your crystal ball. How does the future of the database market start to shake out in the next 3-5 years, and what do you see on the horizon? And that'll be our last question.
A great question. That's something I love to speculate about. There's a great book called The Innovator's Dilemma by a Harvard Business School professor named Clayton Christensen. And basically, he says if you have a legacy solution and the technology changes, it is really, really difficult for you to morph from old to new without losing your customer base in the process. So I'd encourage you to read that book. It's I think priceless, and it illustrates the problem that all of the legacy system software vendors have, which is they're selling obsolete technology for which there's a known better solution, and how to morph from old to new without losing your shirt in the process is something that all of the traditional vendors are going to have to figure out how to do. Another thing that I think is going to be really fascinating is SAP is now in the database business with a system called HANA. There's no question in my mind that a future version of R4 is going to run much better on HANA than it runs on other DBMSs. And it turns out that Oracle is SAP's biggest customer. So the majority of SAP databases, R4 databases, run on Oracle. So SAP wants the Oracle business. Simultaneously, there's no question in my mind that that future versions of the Oracle hardware are going to run Oracle way better than other people's hardware. So the two elephants are going to be duking it out with each other, trying to make their software stickier on their kind of stuff. So I think that will be an interesting trend that we will watch unfold. I think the other thing that's guaranteed to happen is that if you're an enterprise CIO, you're going to be running somewhere between half a dozen and a dozen purpose-built database systems, and how to seamlessly get data back and forth among them. The data integration problem is going to be something you're going to have to face in spades. So I think those are sort of the high-level bits of what I see coming. But I think we live in very, very interesting times.
Excellent. Thank you so much, Mike. And on behalf of Mike and myself and VoltDB in general, we'd like to thank everybody for coming. And I'm going to hand it back over to Yasmina to close us out here.
Great. Thank you so much. Folks, we would like to say a very big thank you to Scott and Michael for presenting an incredible webcast for us all today and for sharing their knowledge and expertise with us. Thank you so much, gentlemen. Folks that attended our webcast today, we'd like to thank you as well. And for many of you, we had people from all over the world joining today. So for those of you that got up early or stayed up late to attend the webcast, we thank you, and we hope you've all benefited from the event. And also a very big thank you to those of you that sent in your questions, because having your questions really adds so much to our events, and we do appreciate it. And as we close out, folks, we'd like to let you know, I'm going to push out a URL here for you. Here it comes. We'll open up on your computer. As well, VoltDB, folks, has provided some really great resources for you all, and you can find those in your green file folder widget, the resource widget. Please open that. Get the information before you leave today. Lots of valuable info there that can really help you with your day-to-day, so do take advantage. And we would like to say a big thank you to VoltDB for sponsoring today's event. VoltDB is an in-memory new SQL database purpose-built to power a new generation of applications that thrive on fast, smart data. Tapping the lightning speed and real-time analytics of VoltDB, organizations are able to add context and intelligence to data the instant it arrives to make real-time transactional decisions that will maximize its business value. The relational database is architected to meet the distinct requirements of fast data, which leads to big data. Organizations in markets such as mobile, financial services, energy, advertising, security, and gaming are relying on VoltDB to process smart data fast to capture new revenue opportunities, drive competitive advantage, and create highly specialized interactions. Thank you again, VoltDB. Folks, this will conclude today's webcast. Goodbye, everybody.